All right, so let's take a look at 6.3, 6.4. This is part 2. It's still looking at exponential functions. Okay. First, can someone remind me, what is the formula that we're using to write exponential functions?
Y equals a times b to x to the power of x.
Yep, y equals a times b to the power of x. If you were looking at a table, how do you figure out what the a is?
By using the number under 0, the
Right.
y value.
Yep, it's the y value that's right below the 0 if you're looking at a table. So for example, in a problem like this, well, they didn't give you a 0. But in a problem like this,
36.
the a value would be 36. Yep. And then how do you get the b value?
You see what the relation of each number is.
You see the multiple of each number.
Right, you got to see what you multiply by each time to get from one number to the
In
next.
this equation would be 6.
Yep, in that equation it would be 6. Now, we haven't done one like this yet, but let's say I gave you numbers like this, 24, 12, 6, 3, 1.5. Does anyone see what you're multiplying by each time there?
You're multiplying, you're not multiplying, you're dividing.
Well, we are still multiplying, but it's just going to be a fraction.
So you're multiplying by 1/2.
1/2, yep. So we haven't done any yet where the numbers get smaller each time for multiplying, but that can happen as well. So that would be multiplying by 1/2, and that's your b value. All right, it's a kind of a review question. How would you write down how the graph of 4 times 5 to the x compares to just 5 to the x?
What's it again?
If you had to write down how those two graphs compare.
Vertical stretch by a factor of 4.
Yep, vertical stretch by a factor of 4. Perfect. All right. How about instead of just having the 4 in the front, you have a negative 4 in front?
Vertical stretch by the factor of 4 and reflect over the x-axis.
Yes. Vertical stretch by factor of 4 reflected over the x-axis. Yep. Okay. So now on your guided notes, it says let's look at other ways to compare exponential functions. All right. So in that last problem I gave you, like I made up those numbers, 24, 12, 6, 3, okay, whatever they were. They were getting smaller each time. Right? And that's because, well, let me show you. On a graph, when something gets smaller, let's do like y equals 1, we'll use that for a, times, let's do 1/2 to the x. So in this case, it's like my b value is 0.5. Okay, watch what happens when I do that. Let me fix that. Okay, what looks different about this kind of graph than the ones we did in the homework last night?
Graph? Oh, instead of it going like from the left side, coming from left side curving up, it's coming from the right side curving up.
Yeah, it's curving, so if you look at it going to the right, it's curving down to the right, and it's almost getting pretty flat. Like the ones we did in the homework last night were flat on this side, and they curved up. Okay? So let's write this down. All right, so there's two numbers that control what these graphs look like, the A and the B. The A is the number in front that causes a graph to either stretch or we could say it can compress. So what would it look like if it compresses? Well, let me show you. Okay, let's say we had a graph that looked like this. If I wanted to take that graph and stretch it vertically, a stretch would look like this. It would take the graph And it's like I'm just pulling down. That's a vertical stretch. And you notice with a vertical stretch, it causes it to be steeper. And when you stretch it out, it gets steeper. If I compress it, it's gonna squish it. Okay, it's gonna get less steep. Let me show you what that looks like. Compression. So this is stretch. This is a compression. It's like I'm squishing it down. And notice what happened to it. It got a lot less steep. It still curves up, but it's not as curving up as sharp. Yeah. Yep. This sign up.
I forgot my ID.
You can type it.
Oh.
All right. So if the number in front, write that down. That's the number we're talking about right here. If that number is between a 0 and a 1, that's going to take your graph, and instead of stretching it, it's going to squish it. All right, let me just make sure that's right. Stretch factor above. You know what? For that one, the way we're going to say it, the graph is stretched vertically. Actually, no, that's fine. You can say it that way. The graph is stretched vertically by a factor of A. So essentially, you're still saying it the same way we did yesterday. So if you had something like this, say y equals 1/2 times 2 to the x, and you were comparing it to this one, how would you describe what the 1/2 does? What's the sentence you would write?
Y equals negative 1/2 times 2 of x.
So this is kind of like when we did the compare in the homework last night. We're looking for a sentence that explains what that 1/2 is going to do. Anyone think they see how to say it? It's the same as what we did in the homework last night. There's no change in how you say it.
What was the question?
How would you describe how this graph compares to that graph?
Wouldn't it be like the vertical stretch
Mm-hmm.
of 1/2?
Yes, this is a vertical stretch by a factor of 1/2. Okay. What you need to kind of keep in the back of your head, though, is if you stretch something by a half, it doesn't really stretch, it shrinks it. We're writing it that way so you can write it exactly the same way you did in the homework last night. Okay. So vertical stretch by factor of a half. Okay. What if I did a vertical stretch by a factor of 3? Would that really stretch it, or would that shrink it? Vertical stretch by 3.
It would stretch it.
That would stretch it. Yep. What if I did vertical stretch by 10? Would that stretch it or shrink it?
Stretching.
That would stretch it. What if I did a vertical stretch by 1/3?
It would shorten it.
Yeah, that would really shrink it. Stretching by 1/3 really shrinks it. Yep.
Anything below 1.
Yeah, anything, what we said right there, anything below 1, right? Anything between 0 and 1 is really going to compress it. It's going to like shrink it. But you still can say it the same way when you write your answer. All right, now let's look at this one. If A is a negative value, okay, so on your guiding notes, right below where it says written like, it says if A is negative. What do you think you still have to say first, even if the A is negative? What do you think the first part of your sentence would be?
Vertical stretch by a factor of.
Yep. So you're still going to start out by saying vertical stretch by a factor of. That's this part you said right here. Stretched vertically by a factor of. But now you need to add the second part, which is what I highlighted in yellow. The negative causes the graph to reflect over the x-axis. So you need to add what's in yellow onto the end right there. And reflected over the x-axis. So no difference from yesterday at all. It's exactly the same thing. All right, so I'm gonna, after you guys copy that, I'm gonna put up a few examples and just have you practice writing the sentences down for how to compare. And then we're gonna do a couple applications with exponential functions. Okay, I think one we're gonna do is from like banking. We'll do something with maybe like interest. And then I think there's one other one. Yeah, we'll take a look at it. Let me see if I can leave those up. Okay, so example 1 has 4 different equations that I'm going to have you guys try to compare. Okay, I'll leave that up. Well, those are the first 3. So it says compare the graphs below to y equals 2 to the x. And remember what I said yesterday, if I'm having you compare to 2 to the x, like that, they're all going to have a 2 to the x in them. They have to. If I gave you a 2 to the x here, and I didn't give you 2 to the x's in the problem, you couldn't do it. It wouldn't make sense. Okay, so take a minute, see if you can figure out what the sentence should be for each of those. Let me see if I can scroll down so we can get D up there. Okay, well do you guys have the directions on your guided notes? Compare the graph of the function? Okay, so I can scroll past those. There you go. And there's the 4 examples you guys can try. Okay, remember, each one of them should start out with vertical stretch by a factor of. And then if it has a negative, you have to add that extra sentence about reflecting over the x-axis. All right, so let's start to look at these and see how we did. Okay, so the first one, it has a 3 in front of the function that they told you to compare it to. How would you explain what the 3 is going to do?
Vertical stretch by a factor.
Yep, so vertical stretch by a factor of 3. Okay, and I graphed that so you could see it. The one in blue, that's the original. The one in red is the one that's been stretched. So it's like you pulled up on it. And that's why it curves up sooner, because you pulled it up, stretched it. Yep. All right. How about same kind of problem, but this time instead of a 3, it's a negative 3. What's the sentence you would write here?
Vertical stretch by a factor of 3.
So it starts out the same way. Vertical stretch by a factor of 3. Yep. And another word, if you don't want to say reflected, you could also say like flipped. That means the same thing. Right? Reflected over x-axis. Right, so that's the one where it curves down instead of curving up. So let me show you what that one would look like. Okay, so the one that it's drawing right now in blue, that's the original. And here's the one that's been stretched and flipped. It's gonna look the same at first, but then it's gonna curve down because it's been flipped. Yep, that's what that looks like. All right. How about this one? Y equals 1/3 times 2 to the x.
Vertical stretch by a factor of 1/3.
So vertical stretch by factor of 1/3. So is that really gonna, that's how we say it, but is that really gonna stretch it? No. All right, if I put that one in just to show you that one, let's do 1 divided by 3, and I need parentheses around that. Okay. So if I put in 1/3 times 2 to the x instead of just 2 to the x, what's going to happen here is it's going to squish it. So it's going to curve up slower. It's almost like this one's going to be underneath the blue one. Okay, let's look at it. So here's the blue one. And now imagine taking the blue one and like squishing it down. Right? It's going to make it flatter. And you'll see that with the red one. It's not completely flat, but it squished it a little. Okay, the more you squish it, the flatter it would get. Okay. All right, and how about this last one? Y equals negative 1/3 times 2 to the x.
Vertical stretch by a factor of 1/3.
So vertical stretch by factor of 1/3. Okay. Yep, and reflected over the x-axis. What causes it to reflect over the x-axis?
Because of the negative.
Because of the negative. Okay. If you put a negative on that number, it causes it to reflect over the x-axis. Okay, we're not going to do this, but if you put a negative over here, it reflects over the y-axis. It flips the other way. Okay, so you can make it flip any way you want, depending on where you put a negative. But that's the key. Negatives make it flip. All right, let's look at this one. So this one, this is on the back of your guided notes. Example 2 at the top, and I think you already have it written down. So it says Noah bought 5 butterflies. And every year, the number of butterflies triples. Now, one thing we are going to assume here, to make it simpler, is that none of the butterflies are dying off. Okay, because if that was happening, it would kind of complicate things. So we're going to assume we got 5 butterflies, and it just keeps tripling every year. So we want to write a function that's going to predict like how many butterflies we would have in 20 years. Again, it's not realistic that they're not going to die off. But, and the hint is to make a table.
Wouldn't it be 5 times 20 to the power of x?
Well, let's see what happens, because we got something in there about tripling, so we need a 3 in there somewhere, okay, to represent tripling. But what's the formula that we've been using all week?
Y equals a times b to the power of x.
Yep. So that's what our answer needs to look like. We need to figure out what the a and the b is, and the hint is to make a table. All right, so write an exponential function where y represents years and b is the number of butterflies. All right, I don't think I want to use y. I think it's just going to be confusing because we're going to confuse y with like the y-axis, and that's not what we want to do. So instead of y for years, let's change y to t for time. So let's use a t, where t represents basically the number of years that have gone by, but it's time. Because I don't want to confuse y with the y-axis here. That'll mess us up. All right, so we need to make a table. Right. Normally in the table we do x and y. Well, they're giving us different letters. They're saying T and B for butterflies. So when we think about the number of butterflies that Noah has, what's the smallest amount of time that could have gone by in this problem?
0.
0, right? That's like 0 always represents the beginning, right? If you're doing like an experiment or something.
So we're gonna be 0 for pizza.
So how many butterflies did he have at the very beginning? That's what 0 represents.
Oh, 5.
5, yep. So when time is 0, that kind of represents
When you bought them.
when you bought them. That's the day one, first second you bought them. All right, now, time is measured in what unit here?
Team.
Well, that's the letter we're using, but what's the unit?
Oh, year.
Years. Okay. So based on the fact that the number of butterflies is going to triple every year that he has them, how many butterflies will there be
15.
at the end of the first year? Yep, 15. And let's just do 2 more. How many butterflies would there be at the end of the second year?
45.
Yep, 45. And we could do 1 more. How many butterflies would there be at the end of the third year?
35.
Yep, 135. Okay. So by making a table, we turn this problem into the kind of problems that we've done before. We can figure out A and B from the table. We learned how to do that yesterday. What's the A value going to be in this case?
5.
What is it?
5.
5. It's always the number that's with the 0. Okay. If it's not called x and y, then you got to remember it a different way. It's the number that's paired up with the 0. So it's 5. So it's y equals, or actually it's not y equals, it's the number of butterflies equals 5 times. And then what's b in this case?
Multiples of B, the array B.
Yep, it's what we multiply by each time to get from one number to
So
the
it'd be
next.
3.
So b would be 3.
3 to the power of x.
And what's our letter that we used instead of x in this
Oh,
case?
T.
We use t. Yep. So t just stands for time. Right. And there's your formula for the number of butterflies. Now, realistically, if none of them were dying off, that would start to be a problem pretty quickly. So if I type that in on the calculator, and look at our table. Okay, the calculator can make a table a lot faster than we can, but it made the same table. 0, 5, 115, 245, 3, 135. Look what happens after just 10 years. Okay, after 10 years, that's almost 300,000 butterflies from just one person, So if this was happening with, butterflies all over the place, that would be a problem. But that realistically wouldn't happen because butterflies would be dying as they're also being born, so it would balance out. All right, so any question on how do we figure out that formula from a table? And the nice thing about, I know we don't use these a lot, we use them a little bit. The calculator can actually figure out that formula for me if we use one of these calculators. It can give me the 5 and it can give me the 3 automatically. All we have to do is type some of that information in and it will figure it all out for us. So that's helpful when, like if you had a table that didn't have a 0 in it. Right now, we don't know how to figure out this number. if I don't give you a 0. You can, but it's a little more complicated, all right? And that's where a calculator could probably help us. Right? But for us, you'll always have the 0, so that makes it a little easier. All right, so now I told you that there were 2 types of exponential functions we were going to study this week. Okay, one of them looks like this, and the other one looks like that. Does anybody remember what that one's called? Where it curves up as we go to the right.
Positive.
Well, what's happening to the y value? As you head to the right, the y value is doing what in this one?
Increasing.
It's increasing. Right? Another word for increasing would be like it's growing. Right? So when you have a graph where the number for A is bigger than 0 and the number for B is bigger than 1, that's called an exponential growth graph. Okay, so on your guided notes, there's a blank line where you need to write in, I think there's a blank line. Yeah, this is called exponential growth. Okay, and the other one we're going to talk about tomorrow, that is called exponential decay. Okay, that's when something decreases. So those are the 2 conditions that have to be met for something to be exponential growth. Okay. So what's the formula that we can use to do exponential growth when they give us what's called a growth rate? Right? We haven't done a problem yet where we've had a growth rate. But we're going to do one in a minute where they tell us we have a percent growth. Okay? In this case, it's going to be 4%. Okay? This is the formula that you need to use when they give you a problem that has a percent in it. Okay? It's y equals a. It's kind of like the formula we had before, but instead of b with an exponent, we have something a little different. We have 1 plus r. And that's because they're giving us the information as a percent. So we have to do it this way. So there's 3 letters in the problem. A is always what we call the initial amount. So like in the butterfly problem, it was 5. So A is always what you're starting at. It doesn't necessarily have to be an initial amount like number of butterflies. It could be an initial amount of money. Like let's say you're opening a bank account and you put $200 in on the first day. That's an initial investment, initial amount of money you put in the bank account. Okay, R is what we call the growth rate. In a banking problem, they refer to it as interest rate. Now, under growth rate, what does it say in parentheses about the growth rate?
It's a decimal.
It has to be a decimal. So if you had something like 12%, does anybody know how you change the percent to a decimal?
Multiply that.
Don't you like have to like move like the 0? It's like
You would
Or no, it's
divide
with
by
the decimal.
100.
So yeah, you divide by 100, which basically takes your decimal point and does what to it?
Move it twice to the left.
Move it twice to the left. So what does 12% become?
0.0012. No, 0.012. Point
0.12.
0.012. Is it not bad?
0.12. Yep. You could say 0.12 or you could say 0.12. So what if you had something like 23%?
You divide by 100 and get 0.23.
0.23. What if you had something like 5%.
You want to just divide by 100 again, and then you get 0.05.
Yep, 0.05. Yep. How about 4.2%?
0.42.
0.42 would be 42%.
0.042.
0.042. Yep. So you always take the decimal place and you move it 2 to the left. That's how you change the percent to a decimal. Okay, so it's very important you do this when you fill in your R. If you don't, it'll come out wrong. It'll be 100 times too big. Right? And then the last thing is T. That is the time. Okay. Generally, the problems we do, they're going to be measured in years. Okay. It doesn't have to be years, but we generally do years. So does everybody have that formula? Let's try example 3. So it says, write an exponential function to model this situation. You're putting $250 in a savings account, and it earns 4% annual interest. How many values did they give me in that problem?
2.
They gave me 2. How many letters are there in the formula, like in this part of the formula on that side?
3.
There's 3. So they didn't give me one of them. Which one didn't they give me?
DT.
They didn't give me T. So then we're not going to fill in anything for T. We're going to leave T as T. All right. So what's the first thing we're going to start out with on the left-hand side when we write this equation?
You would try to solve for 250.
Yep. Yep. So what's the first thing we're going to put on the left-hand side to write this formula?
Why don't you make a table?
No, we don't need to make a table.
Y equals?
Yeah, we're going to start with y equals. That's the first thing we put. In the formula, what's the first thing that comes after the equal sign?
A.
The A, and what does it tell us the A is?
Initial amount, so that would be 250.
It's the initial amount or investment. In this case, it's the $250 that you put in your bank account. Yep. So that's your A. What's going to come right after the A?
Parentheses.
Yes, we put a parenthesis. Okay. Next thing after the parenthesis?
1.
1, yep, the 1, the plus. And what comes after the plus?
A 4.
Well, what comes after it in general?
A decimal.
Yes, your growth rate as a decimal. Yep. So our growth rate is 4%. Remember, you cannot fill in a percent there. You have to change the percent to a decimal. So what would you fill in instead of 4%?
0.04.
Yep, we're going to fill in 0.04. Close parenthesis. And there's one more thing we need, but we're not filling anything in for it.
T.
T. Yeah, we need the amount of time. Okay. So there's only one thing there that we could simplify. Okay. When you follow PEMDAS, what's the first thing you do? Parentheses. All you can do is add up the two numbers in the parentheses. And you should combine those together. Okay, so we'll add those up. Yeah. Okay, so we were talking about in the parentheses. What do you get if you add 1 plus 0.04?
You 1.04.
1.04. And that's the final answer. What they could have done, but they didn't, is they could have said, based on putting $250 in your bank account and earning 4% interest, how much money will be in your bank account after 5 years? So then I would have had a value I could fill in for time. I would have put a 5 in, and then I could do this on the calculator and see how much money I would have. And you would have a little bit more than $250 because if you make interest on your money, that means it's a little bit of money the bank gives you just because you put your money in the bank. Not a lot of money, but a little bit. All right. Any question on that one? So there's no table. You just have to take the two numbers they give you and you just have to fill them in the right spots. But make sure you remember that decimal. All right, so let's try. You know what I do? Does everybody get this one? Because I'm going to delete it. So that way I can put the notes next to the new example. Everybody got it? Okay. All right, so let's try this one. It says, write an exponential function to model the situation. Then, now this is the second part that I was telling you they could add on. Then estimate the value after 4 years. Okay. So this problem is going to be about the population of a school. So right now it's at 10,400. And the population is increasing at a rate of 3%. So the first thing they want us to do is write down a formula, just like we did over here. Well, the problem I deleted. So let's do that first. Okay, when we write our formula, what's the first thing that's going to go on the left-hand side?
Y equals.
Yep, I'm going to start with y equals. I'm going to write it up here because I know there's going to be something that simplifies, and I'll put the final answer on the line below. Okay, so I'm just going to put it up a little bit for now. Y equals, what comes right after the equal sign? Yep, and what is A again? That's the initial amount that you started with. So what's the initial amount that we started with here?
10,400.
Yeah, that's not an amount of money, that's an amount of people. Okay, so 10,400. All right, what comes right after that?
The percentage rate increase.
We got a few things we got to write down before that.
What was the question?
What comes right after the 10,400?
Parenthesis.
Parenthesis.
1 plus no 0.03 parenthesis 2.
So 10,400 parenthesis 1, then plus.
0.03.
And now we have to put in our percent as a decimal, 0.03. And what goes as the exponent? We're not filling in a number for it yet. That's the second part.
T.
Right. For now, it just stays as t. So the answer for the exponential function is y equals 10,400. What's 1 plus 0.03?
1.03.
1.03 to the t. Okay, so that's the first part. Now the second part says to estimate the population of the school after 4 years. So where is this 4 going to get filled in?
At the T.
For the time, for the t. Yep. Okay, well, we'll need a calculator to do this. So we have y equals 10,400 times 1.03 to the 4th power. And you can type that in on the calculator exactly the way you see it, the way I wrote it. So 10,400 times 1.03 to the 4th power. Calculator will handle all the order of operations, PEMDAS, automatic. So now it says to round to the nearest whole number. So after 4 years, how many students will be in the school based on that data? Yeah.
Would he get 1.3?
The,
No, 1.03.
when we added 1 plus 0.03 together.
Oh, I see.
That's the 1.03. Okay, so what's the population of the school going to be based on that growth rate after 4 years?
11,705.
11,705 students. Yep. So that problem took the last one a step further. We had to figure out what the formula was, and then we had to use the formula to make a prediction. Now, that's not a guarantee that there'll be that many students. That assumes the growth rate is going to stay at 3% every year for 4 years. That might not be realistic. All right. Any question before we look at the last problem? All right, so the last problem, you need to copy down that formula. That goes right at the bottom, towards the bottom of your guided notes. This is what's called the formula for compound interest.
Instead of one number, it's exponential.
Yeah. This is more realistically how a bank would pay you interest on your money. It's a little bit more complicated than the last interest one we did. That was called simple interest. It's not really how a bank would pay you, but it's simple to do. That's why we have it. This is compound interest. Okay, without getting too deep into what compound interest is, basically when you put your money in the bank, you have the money you put in the bank, and then you have any interest that the bank paid you. And that interest is added to your bank. It might be added in every month. Okay, you might not get it every day, because that would be a lot of work for the bank to put in little deposits every single day with the interest you make. They may just say, we'll give you all the interest you make at the end of the month, and then they add it into your account. Adding interest into your account, that's what this word is right here, compounded. If the bank pays you interest every single month, how many months are in a year? 12. So 12 would be a common number to plug in for n if you were paid every single month by the bank. Now, what if you were paid every single day
Maybe daily.
on a regular year? What number do you think that would be?
365.
Yeah, n would be 365. If you were paid every week, it would be 52. All right. So they'll tell you in the problem how often the bank pays you. That's what compounded means. A is still the same. That's how much money you put in your bank account. R is still the same. That's the growth rate as a decimal. And T is still the same. That's the time in years. So this is the only new thing, compounded. Right? And just think of that word, it's how often the bank pays you. In general, the more often the bank pays you, the more interest you make. It would be better if the bank would pay you your interest every single day and put it in your account, rather than waiting till at the end of the month. It would be better for you. You'd make more money. Not a lot, a little more money. All right. So let me keep that up. And let's try this. Okay, so as we read that problem, can somebody tell me something something that's important in that problem?
$240.
Yes, that's very important. What letter do you think that's going to be?
A.
That's A. That's how much money you're putting in the account. Okay, so we have the A. Is there anything else there that's important?
9%.
9%. Okay. What letter do you think that's going to be?
R.
That's your R. But remember, you can't write it as 9%. What's 9% as a decimal?
0.09.
0.09. All right. Anything else that's important if you keep reading the sentence?
Find the balance after 3 years.
Something before that we missed that's important.
Annual.
Annual. Compounded annually. What letter here tells you something about compounding?
N.
It's the N. Now I told you monthly would mean every month. That's 12 times a year. Daily, 365 times a year, normal year. This says annually. So if something happens annually, how many times a year does it happen?
Once.
Oh,
That'd be monthly.
oh,
Annually,
annually is 1.
1. Well, that's pretty lousy. That's the worst kind of interest you could have. They're gonna wait until December 31st, and then they're gonna put all the money in your account on that day. So you're not gonna get any money throughout the year in interest. You gotta wait till the very end of the year to get it. Right? So that's the worst case you could have in terms of you making more money. So compounded annually. And then there's one more thing in the sentence that's important.
Find the balance after 3 years.
The balance after 3 years. And what's the 3 gonna be?
T.
T. So all we have to do is carefully plug those numbers in and then type it all in on the calculator. Okay, what's A?
240.
240. What's R?
1.09.
0.09. Okay, what's M?
1.
1. What's N again? 1. So you actually use that one twice. And then what's T? 3. Okay. Let's simplify this a little bit. Let's figure out what that part is. So I don't have.
It's 1.9, 1.09.
Yeah. Right. If you weren't sure how to do it, you just type in 1 plus, and then do 0.09 divided by 1. That's how you could type that in and just see what it is on the calculator. But yeah, it's just 1.09. And we could simplify this. What's 1 times 3?
3.
3. Okay, now I got something a little simpler I can type in on the calculator.
Did you forget the 0
For
for 240?
Yeah, I forgot things. I forgot the 0 right there. 240. Yep. All right, so type that in, 240, parenthesis, 1.09. Make sure you close the parenthesis. That's the button for exponent. It's the same as the calculators I let you guys use. And then it's a 3. So, based on this, if you leave your money in the bank for 3 years and you come back and look at it, instead of having $240, you'll have that much money. With money, how many decimal places does it make sense to round to?
2.
2, right? Because you can have up to hundredths. That's pennies. So if you round this to 2 decimal places, how much money would you have in your bank account? $310 and,
80 cents.
no, not 80 cents.
81.
81, right? That would round up. You might think, what's the big deal, that 1 cent? There's actually a lot of things out there where people that weren't exactly honest in banks, they look at these extra decimal places and they were kind of taking these little fractions of money and nobody noticed because it's such a small amount, the average person wouldn't notice. But if you take small fractions of money from like millions of people, it starts to add up to a lot of money. And then they finally figured out that people were doing that. I don't remember the exact case, but there has been cases where people have tried to do that in banks that work out. Now there's probably computers that might detect stuff like that. I don't know. But, so yeah, the point is it's a big deal to make sure you round properly. All right, so $310.81. Any questions on that? All right, so a couple of reminders. So homework tonight, 6.3 and 6.4 part 2. I'll be after school on Thursday. And the test this week will be on